Assalamu alaikum dear students. I welcome you to 44th lecture of probability and stochastic processes. We have been dealing with Markov chain where an unpredictable time varying random phenomenon is observed at regular properly spaced sampling instances. These sampling instances are predefined and usually at regular intervals of time. So the state of that phenomenon is usually a random variable because we are talking about an unpredictable phenomenon. And all the possible values that these observations are going to give us are called state space, and we analyze the behavior of this random phenomenon as it evolves with time in terms of the states that it visits during its evolution. We studied that there are some states or some values that this random phenomenon takes on initially, but then it evolves in such a way that those states are never revisited. Those states are called transient states. And those states which are visited infinitely often during the evolution of this random phenomenon are called recurrent states. Since transient states are only visited finitely many times, we are interested in average number of visits to these transient states before this evolution takes this random phenomenon into the recurrent class. And we found those numbers using the eigenvectors and eigenvalues of a portion of a submatrix of stochastic matrix describing the whole Markov chain. Similarly, the recurrent states are visited infinitely often, but we are interested in finding how often they are visited. What is the average return time once a state is visited? How many steps the Markov chain spends in other states before that particular state is revisited? And we found that this average return time is inversely proportional to the stationary probability distribution. We analyzed these finite state space Markov chains in terms of transient and recurrent behavior. Then we started talking about those Markov chains where state space is possibly infinite, countably infinite. For these states, we cannot use eigenvectors and eigenvalues because the size of the stochastic matrix is infinite. But we can analyze these types of Markov chains in terms of transient or recurrent behavior and in terms of the average return times to different states. We started analyzing a few simple examples, and today we are going to revisit those examples and analyze them in more detail before we move on to the next topic. Even though I said towards the end of last lecture that we have finished the analysis of Markov chains, but it is important to spend a few minutes and revisit those examples so that there is a smooth connection between the Markov chains and the next topic that we are going to study. So let's have a look at a simple countably infinite state space Markov chain, which is random walk on integers with perfect reflection on the left side. Let's have a look at its graphical model. This Markov chain has states labeled 1, 2, 3, 4 and onwards, all the positive integers or the natural numbers. And transitions from state to state are such that there are only transition to the neighbors. If you are in state 3, you can only go to state 4 or to state 2. There are no big jumps, for example, from 2 to 4 or 2 to 5. So this model is quite simple. The transition probabilities associated with these transitions are that if you are at a state, you move to right with probability P and you move to left with probability 1 minus P. There is one exception though. If you are at state 1, on next observation you will always go to state 2. This state has a perfect reflecting characteristics. The transition probabilities are also shown on the bottom, where P1, 2 is 1, Pi to I plus 1, the right side jump has a probability P, and Pi, I minus 1, the left side jump has probability of 1 minus P. We can simplify this random walk even more by allowing all the integers to be the states. Now the states are 0, 1, 2, 3 all the way towards infinity, as well as minus 1, minus 2, minus 3 and all the way towards minus infinity. And there are only two types of transitions. If you jump to your right neighbor, probability of that happening is P, shown here as probability of I to I plus 1 jump being P, and if you jump to the left, then probability of I to I minus 1 jump is 1 minus P. So this Markov chain is even simpler, and it has a simple structure of jumping to the immediate neighbor on right or immediate neighbor on left. Today we are going to analyze this Markov chain in greater depth, and we are going to find out how this Markov chain behaves for different values of P. Even though we are not going to work with the matrices associated with this countably infinite state space Markov chain, but the entries in that supposed matrix are these transition probabilities where you jump from state I to J, and the associated probability is the I, J entry of that infinite matrix. Here I, J belong to Z, the set of integers. One more thing, if you add all the transitions from a certain state to all other possible states in the state space, the sum is going to be 1. We can extend this concept of random walk from one-dimensional line to two-dimensional plane. Here the possible states are shown here with these ellipses, and they cover the whole 2D plane, and all possible transitions are again to the neighbors, to immediate neighbors on the left, bottom, to right and above. Today we are going to analyze this type of 2D random walk in greater detail, and we are going to assume that all these transitions to upper neighbor, right neighbor, left neighbor or bottom neighbor are equally likely, or they have a probability of 1 by 4. Under this assumption, we are going to analyze the behavior of this 2D random walk on a two-dimensional plane. It's also possible to extend this idea of random walk to dimensions higher than 2. For one dimension, if you jump, you either jump to your immediate right neighbor or to your immediate left neighbor. If you have a 2D plane, then you can jump to your top neighbor, your bottom neighbor, your right neighbor or your left neighbor. And if you think of a space, then you have a levels of grids. There is a three-dimensional grid. So if you are at a state, you can jump towards right, towards left, towards forward, towards back, towards top and towards bottom. It's not easy to visualize random walks on dimensions higher than 3, but you can think this as a collection of n-dimensional vectors, and you jump to immediate neighbor either in the first domain, in the first dimension, or the second dimension or the third dimension, either to a positive jump of size 1 or to a negative jump of size 1. Let's have a look at transition probabilities of all these types of random walks on spaces with dimensions 2 or even more. So if you have a two-dimensional space and you are performing a two-dimensional walk, you are working on a two-dimensional grid. In that case, probability of moving from a vector x to vector y. Here these vectors x and y are two-dimensional vectors. So moving from a certain vector with two entries to another vector is 1 by 4 if norm one of these two vectors difference is 1. That is, you subtract all the elements of y from elements of x, and then you just sum them up. If the sum of absolute difference is equal to 1, then you are moving to either top or left or right or bottom neighbor. You can extend this to dimensions higher than 2, and here x and y are vectors of higher dimension. In that case, probability of moving from vector x to vector y is 1 over 2d, where d is the dimension of the space. And this only happens if, once again, the norm 1 of the difference is equal to 1. That is, vector x and vector y only differ in one location, and the difference is either plus 1 or minus 1. For all these infinite state space Markov chains, we usually restrict our analysis to whether the Markov chain is transient or recurrent, and we do that through this idea of return times. So we find if a certain state is visited infinitely often and expected number of times that that state is visited is infinite, then that Markov chain is recurrent. And if the number of visits throughout the evolution of Markov chain are finite, then that Markov chain is transient. We are going to use this concept of expected value of total returns to that state in deciding whether this Markov chain is transient or recurrent. Let's apply these ideas to the simple Markov chain of random walk in one dimension. You can see on your screen the graphical model of this random walk on one-dimensional line, where we can walk on all possible integers and an associated path. By path, I mean the value of integer where we stand. So if we are on this line, then we are on state 0. When the next transition comes here, we are one step above, so we are in state 1. On next transition, we are one more level up and we are in state 2. The next transition finds us back at state 1, the next transition at state 2, again at state 1, state 2, state 1, and finally 0. So this path shows that during the evolution, this Markov chain has started from state 0 and it has returned to state 0 in 8 transitions. You can see that this is a periodic Markov chain. It's not possible for this Markov chain to come back to the starting state in odd number of steps. You will always need even number of steps to come back. I hope you will understand that the path just shown to you is not the only path where Markov chain evolves for 8 steps and comes back to the starting state. The Markov chain could have gone towards right in 4 steps, and then in next 4 steps it could have come back. In that case, it could have reached a top portion of 4 and then come back to state 0. It's also not necessary for the return time to be 8 to be the first return time. It's quite possible that the Markov chain went up to 2, came back to 0, then went up again and then came back to 0. As long as it is back at state 0 in 8 steps, we'll say that at 8th step it has come back. So the number of steps will be even, and it is allowed for Markov chain to be at state 0 before the 8 is counted. So let's have a look at a few other possible paths where Markov chain comes back to state 0 in 8 steps. So the next possible path is shown here in green, where Markov chain evolves towards left, remains towards left even though it visits 0 here, but goes back to the left side and then comes back to 0. A third possible path is shown in blue, where it goes towards left till it reaches -2, then it comes back to plus 1, again goes back to minus 1, and then returns to 0. So there are many possible paths of length 8 such that you return to the starting state. The condition that this kind of paths must fulfill is that there should be 4 jumps to right and 4 jumps to left, so that overall jumps are 0. Overall displacement is 0 and you come back to the starting state. And this kind of paths are always there for other states. You don't have to have state 0 as a reference. For any other state, these kind of paths will be there because the Markov chain is homogeneous. It is behaving the same way for all possible states. Now let's try to find out the probability of this event happening, that the Markov chain comes back to the starting state in a certain number of steps. We know that these steps must be even. It cannot come back to the starting state in odd number of steps. So if there are even number of steps and the Markov chain comes back to the starting state, then half of the steps will be towards the right and half of the steps will be towards the left. We know that if the Markov chain moves towards right, probability of that happening is p, and if it moves towards left, probability of that happening is 1 minus p. So if there are 2n steps, then n steps are towards the right and n steps are towards the left. But the question is, out of 2n steps, how many ways can we find these n steps towards right and n steps towards left? That is a combinatorics problem, and you know that it is 2n combination with n. So let's find what is the formula for probability of returning to the starting state in 2n steps. The formula for such a return is shown here, that probability of returning from state 0 to state 0, going from state 0 to state 0 in 2n steps, or returning back to state 0 in 2n steps, is combination of 2n, n, then p raised to power n, and 1 minus p raised to power n. For small values of n, we might be able to find this numerically, but if you are interested in analyzing the asymptotic behavior of such a Markov chain, and you want to find if in the long run the state 0 is revisited again and again, then you have to find this expression for very large values of n. And it's not possible to find factorial of large numbers. But we can use Stirling formula, which gives us an approximate expression without this n factorial, and we can use that formula to change this to this new expression. So probability of returning to a state in 2n steps is this expression, which is 2n whole factorial. This expression along with 1 of n raised to power n and 1 of e raised to power minus n for n factorial, and another for n factorial, and this is the old p raised to power n, 1 minus p raised to power n. If you simplify all these equations, you will see that e raised to power minus 2n cancels e raised to power minus 2n in the denominator. Similarly, n raised to power 2n also cancels, and one factor of 2 pi n cancels one of this 2 pi n in the square root, and you eventually end up with this formula, that in the long run, for large values of n, probability of returning to the starting state is 1 over square root of pi n and then 4p 1 minus p whole raised to power n. This 4 comes from expansion of this factor 2n raised to power 2n. The n raised to power 2n cancels with this n raised to power 2n in the denominator, and this 2 raised to power 2n, which is equal to 2 raised to power 2 whole raised to power n, or 4 raised to power n, that is combined with these entries all having p raised to power n or 1 minus p raised to power n. So everything combined here gives us 4p into 1 minus p whole raised to power n. If we want to find out if state 0 is recurrent or transient, we have to take infinite sum of these probabilities of return to the starting state of 0 in 2n steps for different values of n. So we'll take summation over n of these expressions which show the probability of returning to state 0 in 2n steps. Let's take this infinite summation to find out if the result is finite or infinite. If the result is finite, then state 0 is a transient state. And if this result is infinite, then state 0 is a recurrent state. So let's find out. So we are interested in finding the expected number of returns to state 0, and that is equal to summation over n of these expressions of probabilities of returning to state 0 in 2n steps. So summation is shown here. Now start thinking about the values of p. If p is half, then 1 minus p is also half, then this number inside this bracket is 1. 4 into half is 1, and 1 raised to power n is always going to be 1. Hence, summation just reduces to summation of 1 over square root pi n. This summation is shown on this bottom line. So summation of this 1 over pi n whole square root over infinite values of n starting from 0 is going to be infinity. So if p is equal to half, then this summation is going to be infinity and state 0 is going to be a recurrent state. We saw that if value of p is half, then this Markov chain is symmetric in its behavior. That is, it has equal probability of jumping towards its right neighbor and jumping towards its left neighbor. In that case, state 0 is a recurrent state. It is visited infinitely often. And so are all other states, because Markov chain is symmetric and it behaves uniformly wherever you stand. Now let's see what happens when value of p is not exactly equal to 0.5. It is slightly less or slightly more. The expression gives us a clue, and we are going to analyze the infinite summation for value of p not exactly equal to half. If value of p is not exactly equal to half, then this expression p into 1 minus p is going to give us a number which will always be less than 1 by 4. If that number is always less than 1 by 4, then multiplication of that number is going to give us a number slightly less than 1. And if you have an infinite summation of just this part, which is a number slightly less than 1 raised to power n, then this is going to give us a finite result, because of the infinite summation of a geometric series with this r being less than 1 gives us a finite number. It gives 1 over 1 minus r. So if this r is this whole 4 times p times 1 minus p is less than 1, this summation of this factor raised to power n is going to give us a finite number. Let's look at this expression outside. With the presence of this expression, this is no longer a geometric series. Actually, all these numbers in the geometric series are divided by a number which is more than 1. This is square root of pi times n. If this n is 1, 2, 3, 4, 5, 6, then this number is always going to be larger than 1, and this number, which is r raised to power n, is divided by a number which is larger than 1, then this thing is going to converge even faster. So with the absence of this factor, we know this is going to give us a finite number. Then with the presence of this, this is definitely going to give us a finite result, a number even smaller than the infinite summation of this. Hence, the result of this whole summation is definitely going to be less than infinity, a finite number. Hence, This Markov chain is going to be a transient Markov chain if P is any value different from half. This result should not be a surprise, because if you start from state 0 or any other state and you have an equal probability of jumping towards right or jumping towards left, then you may jump towards right for some jumps and then you may come back. So eventually you will come back, and you will come back again and again. But if P is more than 0.5, say 0.6 or even 0.50001, then you have a tendency to jump towards right more often than jump towards left. So if you start from 0, you may jump towards right, you may come back, but you slowly drift towards right. Similarly, if value of P is less than half, it is 0.4, 0.49 or even 0.49999, then you have a less tendency to go towards right and more tendency to go towards left. So if you start from 0, you may come back to state 0 a few times, but eventually you will continue to drift towards left, and then you will never come back to the state 0. Hence, for P equal to half, this random walk on one-dimensional integer line is recurrent, and for all other values of P, this random walk is transient. As I said earlier, you can extend this idea of random walk from one dimension to two dimension or even higher dimensions. So let's analyze the situation in two dimension where you move on a two-dimensional plane which is discretized, which has horizontal and vertical lines, and at the intersection of lines there are states. So you move from one state to one of the four immediate neighbors with probability of 1/4, equal probability. Under these assumptions, we are going to again find the probability of returning to a starting state, say 0, 0. Here the location of the state is indicated by a two-dimensional vector because we are moving on a 2D plane. So let's take the state 0, 0 and find out if we ever come back to that state. Once again, if you want to come back to that state, you have to make same number of jumps towards right as you made towards left. Not only that, you should also make the same number of jumps to top as the number of jumps towards bottom. Only then you hope to come back to state 0, 0. If you apply only one restriction, that you make as many jumps to right as you make to left, but you do not restrict the top and bottom jumps, then you will be at the same location x axis wise, but along the y axis you could be anywhere. So you have to satisfy both conditions. So you have to make even number of jumps towards x-axis on x-axis and even number of jumps on y-axis. So even number of jumps on x-axis, even number of jumps on y-axis means the total number of jumps should be even. It's not necessary for the total number of jumps to be divisible by 4. So it's not necessary for the total number of jumps to be 4, 8 or 16. It's possible to come back to that state in 10 jumps because you move 3 jumps towards right and 3 towards left, 2 to top and 2 to bottom. As long as total number of jumps along x-axis are even and total number of jumps along y-axis are even, you are fine and you will come back to the starting state. Let's find the probabilities of these two events, that is even number of jumps on x-axis and even number of jumps on y-axis separately. So we know that for certain even number of jumps we are moving on x-axis either towards right or towards left. In terms of the conditional probability, you know that you did not move up, you did not move down, so you only moved either towards right or towards left, then probability of such jumps is half because of the symmetry of this Markov chain. So with probability half you move towards right, with probability half you move towards left, total number of jumps along x-axis are even, so what's the probability of returning to the same starting location? And we are going to again apply this rule to y-axis and combine the result. So let's look at just one axis, say x-axis. So if you move back to your starting location along x-axis, then from 0, 0, you could be anywhere on 0, x. So you have moved back to 0, x. Then probability of this event is n combination with n by 2, because total number of jumps are 2n, and out of that roughly half are in x-axis direction and half are along y-axis direction. Hence we are just taking n and n by 2, and here is your half raised to power n by 2 representing the right-sided jumps, and then half raised to power n by 2 representing the left-sided jumps. Because of the symmetry, this is p, this is 1 minus p. If you apply Stirling formula as before, simplify the results, then you will get this expression, which is probability of coming back to the same x location in n jumps, where n is even, and this comes out to be square root 2 divided by square root of pi times n. And this expression is going to be the same for jumps along y-axis. So if you combine this for x and y, the probability of returning to the same state 0, 0 in 2n jumps will be the multiplication of two probabilities, but will have this 1 by 2 outside. Why? Because if you take a large number of jumps and they are even, then it's possible that the division of these even jumps is not even plus even, it is odd plus odd, and you do not return to this starting state. So probability of that happening is almost half, because you are talking about a large number of jumps, and sometimes the division of two jumps along x and y axis, even though close, could be odd plus odd or even plus even. So if it is odd plus odd, this formula is not valid, and if it is even plus even, probability of that is half, and then you multiply the two probabilities of returning to the same x and same y location. If you combine that all, you get this expression 1 over pi n. And expected number of returns to this state 0, 0 during the whole evolution of this two-dimensional walk is this summation, or summation of 1 over pi n, and this is infinity. What does this mean? This means that if we have a two-dimensional grid and you are moving in a random fashion with equal probability towards right, towards left, towards top and towards bottom, then this random walk on 2D discretized plane is recurrent. You will come back to the starting state again and again, infinitely often. Let's think for a moment for cases where jumps towards left and jumps towards right do not have equal probability. Suppose you have a probability of jumping towards right slightly more than 1 over 4 and jumping towards left slightly less than 1 over 4. Similarly, you have probability of jumping towards top slightly more than 1 over 4 and jumping towards bottom slightly less than 1 over 4. Then if you start from 0, 0, you will drift. You will drift towards positive x-axis and positive y-axis. That is the first quadrant of the 2D plane. I leave it as an exercise for you to actually show that if these probabilities are not exactly equal to 1 by 4, then you drift. And if these probabilities are exactly 1 by 4, 1 by 4, 1 by 4 and 1 by 4, then you do not drift, you come back again and again, and random walk is recurrent. Let's talk a little bit about random walk on higher dimensional spaces. We talked about one-dimensional line, two-dimensional plane. Let's talk about three-dimensional and higher dimensional spaces. So if we have a three-dimensional space, that is the 3D space we live in, and it is discretized. There is a grid associated with that. That is, there is a grid on this plane, and there is similar a grid on upper plane and an upper plane. So you can move to right, to left, to forward, to backward, or to top, or to bottom. So there are 6 possible immediate neighbors. So you can move to 6 possible neighbors if you are talking about 3-dimensional space. And probability of these jumps towards right, left, forward, back, up or down is 1/6. And if all these probabilities are 1/6, the Markov chain, the random walk in 3D behaves in a symmetric manner, then what do you expect? Do you think this random walk will be recurrent? You don't have any drifting tendency. All the probabilities are 1/6, to right, to left, to forward, to back, to top and to bottom. All jumps are to immediate neighbors and they have equal probability of 1/6. Then you might say that yes, if you start from 0, 0, 0, that is origin, then you will come back to 0, 0, 0 again and again. Not so. If you have a 3D space or any other vector space with dimension higher than 2 for 3, 4, 5-dimensional space, and you have equal probabilities of jumping to immediate neighbors in any dimension, then this Markov chain is transient. You do not come back to the starting state again and again, and you have a transient Markov chain. It is interesting result. It is kind of unexpected, but there are so many ways you can jump in 3D, 4D and 5D. There are so many possible jumps that it's not possible for you to come back to the starting state again and again. Once again, I leave this as an exercise for you to actually solve this. It's not difficult, and if you fail to solve it, try to consult a good textbook on Markov chains, and the results are right there. Try it, please. So far, we have been talking about Markov chains where the state of the random phenomenon is observed at regular intervals. These regular intervals could be uniformly spaced, say every 1 second, every 1 month, or they could be non-uniformly spaced, but usually they are predefined, well known before the evolution starts. So in case of that person trying to perform Hajj, we sample the state of his application at 3 distinct times per year, and those times need not be uniformly spaced. Now we are going to talk about random phenomena which should be observed at non-uniform sampling instances. We'll talk about an example which will try to analyze using the old method of sampling at uniformly spaced intervals, but we'll see the problems, and then that should serve as a motivation for the next topic, that is a random phenomena, unpredictable phenomena that evolves with time, and we observe its state at non-uniform sampling instances. Let's talk about that example. The example is of a queue, a line. This queue or line could be for customers, where customers come and they join at the tail of the line, and the person at the head of the line is served by the available representative of the business that these customers visit. So this line grows towards this end, but when a customer is served, the whole line moves. So this is first in, first out type of data structure. You also encounter first in, first out data structures in computer science and other applications. So this example is applicable to those cases also. Since we cannot predict when a customer is going to come in, and we cannot predict when the first customer is going to be finishing its business and leaving this line, so we should observe the status of this line at non-uniform sampling instances, but we are going to try to analyze it by using uniform sampling instances. But we are going to take these uniformly spaced sampling instances very close together. That is, we'll take 1 second intervals and we'll assume that in 1 second either one customer comes, one customer gets served, or nothing happens, no customer finishes his business, no customer comes, or both things can happen. But it's not possible in 1 second for 5 or 6 customers to come. If that's the case, then this Markov chain will have a big jump of 5 or 6. So if we assume that this Markov chain evolves slowly, but at sampling instances which are not uniformly spaced, but we observe it at uniformly spaced intervals of 1 second, then this is the graphical model of this Markov chain. State 0 represents that this line is empty. And if nothing happens in 1 second interval, this state 0 remains here. And if one customer comes, it moves from 0 to 1. And if no other customer comes, but that customer gets its service, then it moves back to 0. And if there is one customer and it is being served and the service has not finished, then in next sampling instance, this Markov chain remains in state 1. So after 1 second intervals, this is the kind of transitions that are going to happen. If we have probability of a customer entering a line in 1 second as P and probability of the first customer getting his service, finishing his business and leaving as Q. With these probabilities P and Q, we can find transition probabilities for all these transitions associated with this Markov chain. These transition probabilities are shown on your screen, where P01 represents this transition and it has a probability P. This P is probability of a new customer coming in 1 second interval. So Markov chain moves from empty state to one customer, and probability of that not happening and Markov chain remaining in state 0 is 1 minus P. Other transitions and their associated transition probabilities are shown on your screen. Can you guess if this Markov chain of customers coming and joining the queue and then leaving is transient or recurrent? My guess is that if P is smaller and Q is larger, that is, probability of a customer coming in 1 second is smaller compared to probability of a customer getting service and leaving in 1 second, then this Markov chain is recurrent. It's going to find that on many occasions the line is empty. But if P is larger than Q, then most probably line is going to grow and grow and grow, and it will continue to grow, and this Markov chain will be transient. But we are not going to analyze this Markov chain through this traditional analysis of sampling it every 1 second or 2 seconds or any other regularly spaced sampling instances. This random phenomena of customer arriving and then leaving should be analyzed differently, because customers come at any time. They do not come at regular intervals, and they can come at any time. Hence, we should change our analysis. We should rely on different techniques to analyze the behavior, the evolution of this type of unpredictable phenomenon. Let's have a look at the underlying assumptions, how customers come and how customers leave. Here on your screen, you can see a graph, and this graph shows the number of customers in line. The graph starts at time 0. So here somewhere on this there is a T0, which is when there are no customers. Then this transition is at time t1 when one customer has joined the line. He may have gone to the front of line and he may be getting service, but the total number of customers in the business premises is 1. At time t2, another customer comes and total number of customers is 2 now, which remains so for a long time till time t3 comes and another customer has joined. For this duration from t3 to t4, there are 3 customers. Then the first customer finishes his service and he leaves, and then there are 2 customers, another one finishes and there are 1 that also gets served, and there are no customers from t6 to t7. At t7, another customer comes, at t8, another one comes, at t9, one leaves, and so on and so forth. You can see from this graph that these time instances t0, t1, t2 can happen on any value. They can attain any value, and these transitions can happen at any time. So to analyze this situation, we need different tools. So let's break down this phenomena into 2, that is arrival and departure. If we look at arrival of customers independent of the departures, then this is the kind of assumptions and models that arrival process follows. So at t0, there is no customer. At time t1, one customer arrives. At time t2, second customer arrives. t3, third customer. t4, fourth customer. And this line is going to go on and continue to climb up in stairs, with width of these stairs being unequal and attaining any possible values. So if customers are arriving like this at any possible time, then we have to make some simplifying assumptions so that we can analyze this arrival pattern using tools of probability theory. So here are the assumptions. The first assumption is, of course, that customers arrive one at a time. So this staircase always rises by a standard height. It does not rise in 2 or 3 times that height, because customers do not arrive in groups. And average rate of arrival remains constant, that throughout our observation time, the rate of arrival, the average rate of arrival is constant, and that is lambda customers per second. You can replace second with any unit of time, say minute or hour, but the rate remains the same. You cannot analyze behavior where the rate of arrival of customers in the morning is more, at noon time it's less, and in the evening it's again more. You have to assume a simplifying assumption of a constant arrival rate. Another condition is that probability of arrival in a short interval of time, delta t, is lambda times delta t. So if delta t is very small, and it's possible that in that interval delta t, a customer may have arrived or he may not have arrived. If you take this delta t slightly larger, then probability increases. Hence, the probability of a customer arriving in delta t is lambda times delta t. Please remember, you cannot take this delta t to be 1 second or 5 seconds. Probability cannot be 1. It can be 1, but it certainly cannot be 5. This is only valid if delta t is very small. And the last assumption is that customers arrive independent of each other. They do not arrive in groups, and their arrival does not depend on each other. Under these simplifying assumptions, we can analyze the behavior of this arrival of customers in 2 ways. The first is, we want to find the probability of k customer having arrived in a certain time duration t. That is, at 0 time there were no customers, and then we start our observations at time 0 and we stop at time t. Then what is the probability of k customers having arrived in this duration of 0 to t? And that expression comes out to be this. I'm not going to go through the derivation of this expression. you can consult any good book on Markov chains, continuous time Markov chains, and you will find how this is arrived using binomial theorem. This probability distribution is of Poisson distribution. So number of customers that arrive between 0 and t is a Poisson distribution. Another thing that we can analyze is the inter-arrival times. So a customer arrives at T1, T2, T3, and you take T2 minus T1, T3 minus T2. All these inter-arrival times, they are going to be random variables. And for any of these inter-arrival times to be larger than a certain time t, the probability of that is e raised to power minus lambda t. If you look carefully at this, this is opposite of the CDF. CDF is probability of a certain random variable being less than or equal to the parameter t or x. So here it is opposite to that, minus of that. Hence, the CDF of this probability distribution will be 1 minus e raised to power minus lambda t. Hence, these random variables inter-arrival times are distributed under an exponential probability distribution. So number of customers that arrive from 0 to t are distributed with a Poisson distribution, and inter-arrival times are distributed with an exponential distribution. So if you analyze the arrival process under the assumptions that I have shown to you, then there are two probability distributions that describe this arrival process. The number of customers that arrive between 0 and t given by a Poisson distribution, and inter-arrival times given by an exponential distribution. You can apply a similar analysis to the departure process, where customers are getting served and then leaving the queue. And you can combine these two analyses and get the final result, which describes the behavior of this type of Markov chain, which changes its state at any time. It does not change its state at regular intervals of time, but it changes its state at any values of time. In next lecture, we are going to perform such analysis to describe the behavior of a few simple cases of continuous time Markov chains, where Markov chain makes its transition at any value of time. Till then, I wish you the best. Thank you. Khuda Hafiz.